Welcome! In this video, we'll begin discussing the third case in the WKB or semiclassical approximation. Now, this case is when the energy becomes comparable to the potential, because what we had been seeing before were cases like in the classical region, where our energy was always, right, the energy here in red was always greater than the potential here in green. We also saw the non-classical region, which is when the energy is always smaller than the potential. But now we will begin discussing this region right here, or basically problems where we include that region, whereas where we transition, we go from one to the other, and for that reason, the energy and the potential will become the same. And why is this an issue? Well, because both of our formulas had either 1 over the square root of the momentum or of the absolute value, but either way, they both depended on the momentum. And what is the momentum? Well, we defined it as the square root of 2m, and then we had, depending on the case, v minus e minus v, doesn't matter. The point is that since they will be the same, our entire product will be 0. So we will get 1 divided by 0, and that is trouble. So basically our entire approach blows up if the energy and the potential become comparable. So we need to find another way to deal with this problem. Now, let us call the point where this intersection occurs. In general, you can just call this x2, right? That is the turning point. We also discussed the turning point in Gamo's version of the radioactive decay in another video. But since we can choose this axis wherever we want, let's just call x2 0, and at the end of the problem I will just plug back x2 in there so that we can, have a formula for any case, but of course it doesn't matter. Okay, so let us now begin discussing how do we patch these regions. What do we do here? Well, the answer is precisely there. We patch it. We will now create a zone here in the middle, right somewhere here. We will have some region in between where we will have a special wave function. And what we will do later, we will find this patching wave function, and then we will apply a condition. We say, okay, as x grows larger and larger, we want this patching wave function to become asymptotically equal, or right, approximately equal to our wave function in this region. Let's call it region number 3, since, this is 1, the patching region would be number 2, and this is number 3. So we want this to happen. So this is something that we will use later. And similarly, as x becomes smaller and smaller, we want our wave function in region 1. This is, by the way, what we already found, right? The wave functions in region 1 and 3 are what we found in the previous videos. This is the case where the energy is greater than the potential, and this is when the energy is smaller than the potential. So we already know what those look like. So as I was saying, we want that asymptotically, this wave function in region 1 should be the same as the patching wave function. So we need to find the patching wave function. That is our first challenge. And then we need to patch it together, basically apply boundary conditions with our two already known functions for the two known cases. Okay, one more comment. Notice that I drew my potential, right, as some arbitrary curve sloping upwards, right? I could have chosen some curve sloping downwards. And as you will see in a moment, those are two different cases. And I will make an entire video dedicated to this other case. That is also a problem in Griffith's book. That's why I want to do it separately. Okay, now the results are basically the same. Okay, so I will even show you basically what happens there, but just so that you know. Now, how do we find this patching wave function? Well, let's see. Let me show you how we can approximate. Let us see this potential. Now, it is curvy, right? It is a curve, but if we zoom in, right, we just zoom in, this is basically a straight line. So for that reason, we can say, all right, this is a straight line at height e. So let's write this potential. So let's write v of x as a straight line. So approximated, of course, this is valid around our x2, which in this case is 0. This will be approximately e plus v prime, right, the derivative at that point, times x, right? This is the slope. This is simply because of the fact that we are up here and not down there. So we simply made this equation for the straight line. And this is, of course, where there would be a difference if we were sloping downwards. In that case, we would have a minus sign here instead of a plus sign. Okay, so now we want to find the wave function in this region. How do we do it? Well, we want to find the wave function in the region with this potential. We use the Schrödinger equation. So minus h bar squared divided by 2m, blah, blah, blah. We already know this. And then the potential is E plus V prime of 0x. This is equal to, oh, I almost forgot about the wave function here, psi equal to E psi. Of course, all of these psi's are the patching wave function, right? Now, the energies cancel each other out. And we get d squared psi p dx squared. This is equal to minus 2m over h bar squared. Right, we can divide, not divide, but rather subtract this quantity, minus v prime of 0 x psi of p. And this we just multiply through, so we get 2m over h bar squared v prime 0 x psi of p. And here we will define, because we don't really want to be dealing with this constant, so let's just call it some alpha cubed. And why alpha cubed? It will become apparent in a moment. You can of course just call it alpha, and then at some point you will find that this was convenient. It doesn't matter at all. So this will be 2m v prime of 0 h bar squared. So our equation becomes d squared, the patching wave function, x squared. This is alpha cubed of x psi of p. So this is the differential equation that we have to solve. However, at this point, it is a bit hard to notice how we can solve it. Let us use the change of variable z is equal to alpha x. And here comes to play why we called it alpha cubed. Because if we want to now see what happens to this dx squared, right, we basically have to write this as d squared psi of p dz squared times dz squared dx squared. But what is that? dz dx. This is simply going to be alpha. So we get this thing squared, basically, right? So for that reason, we get alpha squared. And on the right side, we get alpha cubed, which is alpha squared times alpha times x. But alpha x is simply z. And then we divide by alpha squared, and there we go. This is the equation that we want to solve. And unfortunately, this is, or fortunately, this is the Airy Differential Equation. And this is a relatively difficult equation to solve. I will make a separate video about how to solve it at some point. I will give you just a few hints here in case you're interested. So you could, of course, solve it via a power series, but that solution will not really be useful. We need an integral representation of the solutions. How do we find them? By solving this using a Fourier transform. That will yield one solution, however, not two. It will give us one solution, which we will call AI. These are the Airy functions of the first kind. And the reason why it doesn't yield a second one like this is because the second solution, the BI's, they don't go to 0 as z goes to infinity, which is a requirement for the Fourier transform. So you have to there use a generalized Fourier transform, so you can see, and then apply a complex integral, a contour in the complex plane for that integral, and it becomes really messy. Another way to solve this is to apply, like, I think it's 3 changes of variables in a row, and then you end up with a Bessel differential equation of order 1/3. So that is another way to solve it. Either way, as I mentioned, this is way beyond the scope of this course. Honestly, even though I usually do every single step, I think that this is really not necessary for you to know. And if you're learning this for the first time, I don't think that you should go that deep. Worry about the rest, and then if you're really interested, go into the Airy equation. As I mentioned, I will make a video about it eventually, and once I have it, I will post a link in the description in this video. Or you can check my playlist on mathematical methods, where I'm always updating those videos. Okay, either way, the solution will then be, so psi of p will be some constant small a times the Airy functions of the first kind plus some other constant b times the Airy functions of the second kind. Now, you can rewrite this in terms of alpha x, of course. Bi of alpha x, just to be very clear. Now, what do these expressions look like? Now, let me just look them up here real quick, because I don't know them by memory. So they are the following. AI, maybe I'll put it a little bit to the side. So AI, this is 1 over pi integral from 0 to infinity of cosine of s cubed over 3 plus sz ds. So here you can see, of course, the influence of the Fourier transform, right? This 1 over pi, the integral from 0 to infinity. The 2 here went away when you use the fact that cosine is even. So instead of going from minus infinity to infinity, it goes from 0 to infinity and twice that amount, which cancels the 2. Just a really quick explanation, but you don't really have to worry about where this comes from. Okay, this is just in case you were interested. And bi, this is 1 over pi. You can see a very similar shape. And then you get e to the minus s cubed over 3 plus sz plus sine of, let's see, the same thing. So s cubed over 3 plus sz, and all of this ds. Now, these expressions are rather ugly, as you can see. They are hard to work with. So we are going to be using the asymptotic forms. Again, don't worry where these come from. I will add a video about it eventually, but it goes beyond the scope of the course. So what we will do is we say, well, what we want, as I mentioned, is that as our x increases, which is the same as to say that when z increases, we want our patching wave function to turn into this other wave function. So what we will do is take asymptotic solutions. So 1 for the case where z is much smaller than 0. So basically, when it is a negative number that is increasing in magnitude. And we will also have a case when z is a positive number that is going to be increasing in magnitude, right? And they become relatively large. So in the case where z is much smaller than 0, we have ai is 1 over square root of pi minus z to the 1/4 power, and then sine of 2/3 minus z to the 3/2 plus pi over 4. And then bi will be relatively similar, so it is 1 over square root of pi minus z to the 1/4, and then the cosine of the same thing. So cosine of 2/3 minus z to the 3/2 plus pi over 4. So let me just rewrite this 4 here so that I don't make a dumb mistake later. Okay, and now I'm gonna move this to the side. Now in the other case, so this is of course in the negative region. Now in the positive region, so when z is greater than 0, what do we have? Well, in that case, we have a I of z. This is 1 over 2 square root of pi z to the 1/4 e to the minus 2/3 z to the 3/2. And bi, well, these are all, of course, approximate solutions, of course. And bi of z, this will be approximately 1 over square root of pi z to the 1/4 times e to the 2/3 z to the 3/2. Whew. Okay, so those are the solutions for our Schrödinger equation. Okay, so don't worry too much about where they came from. They are simply the solutions. So we plug them in there. Okay, so now that we have that, let's go back. Let's keep in mind our procedure was 1, find psi p, the patching wave functions. 2, apply these boundary conditions, right? That we needed the patching wave functions to turn into our wave functions in regions 1 and 3. So let's write down explicitly what our wave functions were. So what we found previously, right, was the following. This was in terms of x. This is in the previous videos. We found that for the region 1, our wave function is 1 over the square root of p of x times, actually maybe let's use this parentheses, some constant e to the, and we had plus or minus, but I will write them down separately. So let's begin with the positive one. So be e to the I h bar integral of p of x dx plus c e to the minus I over h bar integral of p of x dx. But what are the limits of the integral? Keep in mind that we had a lot of freedom to choose them. So we are in region 1. So we can integrate from some x here all the way to 0. So, let's choose that. So these integrals will be from x to 0. So to avoid confusion, let's write x prime and x prime, x prime, x prime, and x to 0. So this is the first form. So this is region 1. So just to be very clear. And just to be very, very clear, this is where x is negative, right? So x is negative. And where x is positive, we have p of x. And then we get, so our solutions were of the form some constant, let's call it d, e to the plus or minus 1 over h bar integral of p of x, but absolute value, dx. Now, notice a few things. So, well, let's write this out. So just as before, we get one positive integral and one negative. However, we are in the region here where x is positive. And what is going on? What we expect, since the energy is less than the potential, we need some sort of exponential decay. We cannot have that the wave function is exponentially growing. That makes no sense. So for that reason, we cannot have the positive solution. We can only keep the negative solution. Okay, and we now integrate from 0 to some arbitrary x, right? So there is the reverse from before. We integrate, just to show you, from 0 to some arbitrary x. Okay, and notice that if we were in the other case, if we were in the case where the slope is downwards, then our two cases would be reversed. So we would have the classical region, right? So this part right here is the classical region. We would have the classical region down here, and the non-classical region, which is this, we would have it right there. So basically we would have almost the same thing, except that we would have for negative x this thing, and for positive x, so x positive, we would have this thing. Okay, so some slight differences. Okay, but we will see that case in more detail, so don't worry about it. It's just in case you were wondering. So now we have psi of x and psi patching, right? We have psi in general and psi patching, but we want them to be equal. So psi 1 has to be equal to psi patching in the limit where z is much smaller than 0. So let's begin with that case. Now, note though that we do need to find the momentum first, right? We need the momentum, we need its integral. So maybe let's take a breather, and before we do this, let's just go off to the side and calculate the momentum and its integral. So what we had was that the momentum was square root of 2m e minus v of x. But let's remember, what was v of x? We said that we are going to be in the patching region, this e plus v prime 0 times x, right? And then we're going to be moving away, but this is what we will be working with in the patching region, where, keep in mind, psi 1 also is in this patching region, right? So if we take this potential, it is still valid for some region. And then as we move away, we want both wave functions to be the same. And the same logic, of course, applies for region 3. So this will be square root of 2m e minus v prime of 0 x. So the e's cancel out, and we get that the momentum is going to be square root of 2m v prime of 0 times minus x. But notice that this thing, it might look familiar, and if it does, it's because we have already seen something like this. We saw that alpha cubed is 2m v prime of 0 divided by h bar squared. So if we multiply and divide by h bar squared, so times the square root of h bar squared, square root of h bar squared, we get that the momentum is, here we have our alpha cubed, so alpha cubed, and then we have minus x, and we still have an h bar that we can just take outside. So basically, this is h bar alpha to the 3/2, and then minus x to the 1/2. Notice that this isn't a problem at all, because the only place where we get only the momentum is when x is negative, which means that this thing is positive anyways, so we don't need to worry about it. So what happens with the absolute value of the momentum? Well, the absolute value of the momentum we encounter in the region 3, and in that region x is positive. So for that reason, we get here we can write this as square root of minus 1 times x. So this is basically h bar alpha 3/2 times I and the square root of x. So basically and we have to take, of course, this. So the absolute value of the momentum is simply h bar alpha to the 3/2 square root of x. Okay, so let me highlight our results. And what about the integral? So we need to find the integral from x to 0 of p of x dx. Well, this is primes, of course. Now, p of x is this thing right here. So integral from x to 0 of h bar alpha to the 3/2, and then minus x prime to the 1/2 dx prime. Okay, and well, let's integrate this. This is relatively simple. So h bar alpha to the 3/2, and what we have now with the integral itself, we get minus x prime, and then we have to the 3/2 times 2/3, and because of the chain rule, we get minus 1. And of course, this is evaluated between between x and 0. Now, what does that give us? So at 0, this entire thing is 0. So we are left with minus this thing evaluated at x, but we already have a minus there, so the minus cancel out, and we get 2/3 h bar alpha to the 3/2 times minus x to the 3/2. So there we go. Now, what about the other integral? So integral from 0 to x of the absolute value of the momentum. Well, the absolute value of the momentum is h bar alpha to the 3/2, and then we integrate just the square root. So this is simple, alpha to the 3/2 x to the 3/2. There we go. So now we have everything we need to plug into this thing right here. So let's just begin, as I mentioned, with region 1. So what we will now do is simply apply boundary conditions. We want our patching wave function to be the same as our wave function in region 1, and we will do the same for region 3 very soon. So what is wave function for region 1? Actually, let's take a look at which region is more convenient before we just dive into this. Because what we will do is equate this entire thing equal to, this is region 1, so it will be this and this. But if we start off with region number 3, it will actually be much simpler because we only have one term here. And we will be comparing this with both of these, right? And we will immediately see what the value for small b must be, right? So don't worry if you don't really know why I choose region 3, it will become apparent immediately. The main idea is that because there's only one term here, it will be simpler. Okay, so instead of doing this case then, let's do case 3. So 1, 2, 3, and that is the case where z is positive and very large. Okay, so let's see. So this thing would be, so psi 3 of x, this is 1 over the square root of the absolute value of the momentum, which is this thing right there. So we get square root of h bar alpha to the 3/4, and then x to the 1/4. And then we get d e to the minus 1 over h bar, and the integral that we have right here. So we get h bar. Oh, we forgot about we forgot about the 2/3 here, by the way. I will add a comment there in the video so that you guys know. So I forgot about the 2/3. Okay, so 2/3 and then alpha x to the 3/2. And this has to be the same as our patching wave function in the limit where z becomes very large. So that has to be the same as the sum of those two. So as a, right, just a reminder, this is a patching wave function, okay, this thing right there. So that has to be the same as a times this, so divided by 2 square root of pi, and then z to the 1/4, which is alpha x to the 1/4, e to the minus 2/3, and z to the 3/2 is alpha x to the 3/2. And then we get plus b divided by square root of pi and alpha x to the 1/4, e to the 2/3, and then alpha x to the 3/2. Okay, so now, well, we can of course simplify the h bars here, and notice what we have. There is a positive exponent here, but there is none here. So b has to be equal to 0. It is the only way to match these two wave functions. And then the thing that goes with the negative exponents, we also can put together. Maybe let's write it like this so that it's e to the minus that. So by doing that, we get that d divided by h bar alpha. Now let's write alpha to the 3/4 power as alpha, the square root of alpha, times alpha to the 1/4, because that way it looks the same as what we have on the other side. So this is equal to a 2 square root of pi alpha x to the 1/4. So here, notice that these things cancel out. So we find our first condition, which will be, now we can either choose to find A or D. But notice that what is our goal? Our goal is to connect these two, right? These two parts of the wave function. We want to connect them by finding B, C, D. We can find one through normalization, but we can't find them all like that. So what we want to do is not have this in terms of A and B, small a and small b, but rather in terms of D, B, or C. So, we can just choose D, for example, because it would be much easier to normalize this wave function than to normalize this wave function, right? So for that reason, I would just choose D. So let's here say A is equal to 2D and then square root of pi h bar alpha. So that later, when we also find A is equal to something B and something C, we simply set A equal to each other and we can immediately connect our constants. So that is it for this region. As you can see, this was not very difficult. We can now do the same for region 1. So in region 1, we want this to be the same as our patching region when z becomes much smaller than 0, right? As we go far away from the patching region, we want the wave function to turn into our wave function 1. So wave function 1 is this thing right there. Let's write it down. So wave function 1, and this is 1 over the square root of the momentum, which is square root of h bar alpha to the 3/4, and then minus x to the 1/4. And then we have, let's see, so then we have b e to the I h bar integral, and then c. Okay, so then we have b e to the I over h bar and the integral, which we already solved, so that is the integral, this one, so 2/3 h bar alpha blah blah blah. So 2/3 h bar alpha 3/2 and then minus x 3/2, and then the same thing but with a negative, so c e to the minus I over h bar 2/3 h bar again, and then I'm going to write this as minus alpha x to the 3/2. That saves me a little bit of time. And this has to be equal to our patching wave function evaluated when z becomes very, very negative. So that would be, let's go back here. So that would be, of course, a times ai plus b times bi. But in this region, which is this one right there, first of all, we know that b is 0, so we don't need to worry about this. We only need to worry about this part. So that is, okay, it's kind of hard to copy from here, but 1 over the square root of pi, and then we have minus z to the 1/4, so minus alpha x to the 1/4, and then we have sine of 2/3 minus alpha x to the 3/2 plus pi over 4. There we go. And this, of course, times small a, right? Times small a, because what we did was plug it in here. So, of course, we need to consider this. And just a reminder, b is equal to 0, right? That's something we found before. There it is. Okay, so we now need these two things to be equal. However, one is in form of exponentials, one is in form of sines. So we need to rewrite one of them. The easiest thing is to just rewrite sine, because there's only one sine and there are two exponents. So let's do this as a. So we will just keep it as it is, minus alpha, blah, 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 no change. And the sine is simply e to the 2/3 times I, of course, there's an I now, and then minus alpha x 3/2, and then we have this pi over 4, which we can, this is plus pi over 4, but we can also write this as multiplying another exponent, so e to the I pi over 4. It's the same. And then minus e to the minus 2/3 I minus alpha x to the 3/2. And then we can write this as plus pi over 4, or we can write this as times another exponent to the minus I pi over 4. And all of this divided by 2i. Okay, so now we need both of these things to be equal, right? That has to be equal to that. So let's begin equating the positive exponent with the positive exponent. So when we do that, so positive exponent, we get 1 over the square root of h bar alpha to the 3 over 4, but alpha to the 3 over 4 is the same as square root of alpha times alpha to the 1/2. And then we have, sorry, to the 1/4. And then we have minus x to the 1/4, and all of this times b. So maybe just get rid of the 1. There we go. And this has to be equal to, and now let's take a look at it. So then we have this thing, so a square root of pi minus alpha x to the 1/4, and then we have 2i, so 2i here as well, and also e to the I pi over 4. Okay, so we have this, that. Okay, so now let's take a look at this. This and this cancel out. So when we find a, so a is equal to 2i times b times e to the minus I pi over 4 divided by, oh, actually let's do it like this. So let's write it as square root of pi divided by h bar alpha. So here we have another very nice expression. Yes. Now let's go for the negative exponent. So the negative exponent. So basically equating this part and this part over there. So by doing that, we get, let's see, c divided by square root of h bar, square root of alpha, right, separating this alpha to the 3/4, times minus alpha x to the 1/4. I'll just write them together because we know that they're going to cancel out just like they did a few moments ago. And this has to be equal to a divided by the square root of pi minus alpha x to the 1/4, and then times, oh, there's a minus sign there, by the way, don't forget about it, so minus, and then e to the minus I pi over 4 divided by 2i. So from this, let's now find a. So a is going to be minus 2ic e to the positive I pi over 4. And let's see, this and this cancel out. And then we have square root of pi h bar alpha. So there we go. Now we can connect every single constant, right? And we, as I mentioned, our objective is to get rid of b and c and replace everything with d, because we can find it by normalization, and integrating this is much easier than integrating that. Okay, so we have our other result up there. Let me just take it down quickly. Okay, so now let's just equate everything. All right, so we have, maybe let's begin by equating these two here. So 2d, the square root, has to be equal to that thing. So minus 2ic e to the I pi over 4 and this square root. So the square root immediately cancels out, right? So this and this. And then we are left with c is equal to minus, okay, so the 2's cancel out as well. So we multiply by minus, we also multiply by I. But when we multiply by I, we get I squared, which is another minus sign. So this ends up being positive in the end. So we multiply by I and minus, let's see, do we need to multiply? Okay, I don't want to make a dumb mistake. So if we multiply by I, this minus becomes a plus, so we don't need to multiply by minus. Okay, so we basically get I d and then e to the minus I pi over 4, right? Because this minus turns positive the moment we multiply by I, so we don't need to worry about it. Okay, that makes sense. There we go. Now, let's equate these two so that we can find b in terms of d. So 2ib e to the minus I pi over 4 and the square root. This is equal to 2d and the square root. So the square root, of course, cancels out, just as it did a few moments ago. So 2 cancels out, this cancels out. So we get that b is equal to, now we multiply by I, and we get a negative, which we need to put to the other side. So we get minus I d e to the positive I pi over 4. There we go. Now we have c and b in terms of d. So this was our goal. We accomplished it. Now we can plug everything back into our wave function right there. So maybe let's copy it. So something like this. Let me carefully select it. Now copy it. There it is. Okay, good enough. Good enough. Okay, now let's plug in b. So we know what b is. Now, notice that we will now go to the general case, because before we were working with the case where the potential was E plus V prime of 0x, right? But now we will just leave it in general. So for that reason, we won't substitute here the values for x. Or for p of x and this integral and all of that. Because we now have this general result. These wave functions are valid everywhere. The condition were only for the patching region, okay? So now we are going to have a solution that is valid everywhere. So let's see. Now b is minus id, so we get minus id and then e to the I pi over 4. And then we get e to the I, and then what was it? Over h bar, integral from x, and now not to 0. Let's, as I mentioned at the beginning of the video, now we will undo this choice of axis, so just x2, right? The turning point. If it is 0, then it's the same as before, but this is more general. Okay, and then p of x prime dx prime. So I'm simply plugging it in and making this a bit more general. And now we get plus c times the other exponent. But what was c? Well, c is id and the e to the minus I pi. So id e to the minus I pi over 4, e to the minus I over h bar, integral from x to x2 of the momentum dx prime. Okay, and well, we don't need to change this other one, but what we have up here? So notice we can factor out the i's and the d's, so we can factor out id, so we get id. Now, how can we further simplify this? Well, notice that this is e to the I something plus e to the, or with a negative, so e to the minus I something minus e to the positive I something. And it is the same thing. So if we factor out a minus sign, we get this thing positive, this thing negative. And this is looking very much like a sine. So, right, so the sine of, I don't know, theta is e to the I theta minus e to the minus I theta over 2i. And we have the exponents here, but we need to multiply by 2i, right? So to create that, we can multiply and divide by 2i. And what we will have, let's see, this 2i goes inside, this 2i stays outside. So we get here 2i squared. The I squared will cancel out the minus sign, so we get 2d. And then with this 2i inside, we will have the sign of all of that. So we will simplify our expression considerably. So we get sine of, and now we have 1 over h bar, integral from x to x2, and then p of x prime dx prime plus pi over 4. And we close this and that. And in the lower integral, all that changes really is this x2 now that we are in a more general case. And these right here are the famous connection formulas. And notice that all we now have to do is solve this integral, and that's it. Solve this integral, and that's it. Right? Of course, this is limited. This will help us find the energies, as I will show you in a later video. For the case, we still haven't really shown what exactly to do for the transmission coefficients. And this is also for when we have a downsloping potential. Right? If we have a more complex potential with several changes, we will have to, combine both techniques. We haven't seen the other one yet, but the procedure to see or to find the other case is very, very, very similar. It is in fact the same procedure, just a slightly different result. So that is this technique. This is the important result. This is what you should understand and use. As I mentioned, there's still a bit more to find, but that will be a problem for another day. So I hope that this was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.